Have you ever heard of the show called Name That Tune? Well, the goal is to get to the least number of notes and then try to name that tune based on those notes, maybe 2 or 3. Well, in our previous video, we took a look at Inter-VLAN routing using 2 routers and 4 interfaces. Well, I could name that tune with 1. What do you mean, Keith? 1. We can get down to just 1 physical interface and 1 router and still do all the routing for our network. That's what router on a stick is all about, and that's what this video, based on your request, is all about too. Let's get started. So when configuring a router on a stick, we still have the same requirements as we had previously. For example, this PC right here, its IP address is 10.0.0.10. It's on the red VLAN, which you'll remember from our previous video is VLAN 2. And it needs a default gateway. The default gateway it's going to use is 10.0.0.2. So it needs to have access to a local device that has the IP address of 10.0.0.2 in that same subnet. We also have the server over in VLAN 3, the green VLAN. It has an IP address of 30.0.0.10, and it's using a default gateway of 30.0.0.3. Now here's the crux of the matter. Instead of having a router with a physical interface, 1 physical interface in VLAN 3 and another interface in VLAN 2, we can take 1 router with 1 physical interface and logically subdivide it. We can create logical interfaces. One that would be in the red VLAN, VLAN 2, for the benefit of this client and all the other devices on this subnet, and another logical subinterface that would be in VLAN 3 for the benefit of this client and all of the other devices on that subnet as well. Now here's the fun part. It is so easy to configure this and get it all working. We have 2 parts. Basically, we have to configure the switch port here to communicate with the router, and we're going to configure the router's interface and sub-interfaces over here on R5. So here on this interface right here, FA1/15, we're going to configure it just like a normal trunk port. In fact, if we squint, we wouldn't see any configuration change on 1/15 compared to 11 and 12 and 13 and 14. They're all simply just trunk ports. So let's go into configuration mode and do exactly that. Interface for FA1/15. We're going to say switch port trunk encapsulation. If you're going to be a trunk, we want you to use .1Q. And guess what? We want you to be a trunk. We're going to specify that switch port mode trunk is on so that we don't negotiate or anything else. We're going to simply be a trunk. And that's it. Now our configuration on the switch to support the trunked sub-interfaces of R5 is already in place. What's next? Well, the next thing we do is go over to R5 and configure FA0/0. One of the key elements of configuring R5 correctly is moving to the correct console for R5. So I'm going to go to R5, so we're at the console port for R5, and let's simply talk about for a moment a couple of the details. Number 1, on this physical interface, it has to be up. If the physical interface is shut down, it doesn't matter how many sub-interfaces we create, they will all be ineffective because the parent, the physical interface that's supporting those logical interfaces, has to be up. So we're going to bring up that physical interface. Then we're going to carve out logical sub-interfaces. And here's how you do it. We go to FA00.2, press enter, and poof, the moment we press enter, that sub-interface is created and it exists. Then we tell that sub-interface, dear Mr. Sub-interface, you are responsible for handling any frames that come into this interface if they are tagged with the .1Q tag of VLAN 2. And we have another sub-interface of FA00.3 that says you are responsible, Mr. Sub-interface 00.3, which is just a number here. It's this VLAN tag that we need to really pay attention to because that is what causes this sub-interface to pay attention to those .1Q frames. And we have respective IP addresses for those subnets. So everybody in the red VLAN is on the 10.0.0 network, including this logical sub-interface, which happens to be the default gateway of this PC. In VLAN 3, we have the network of 30.0.0, which matches the 3-octet prefix that the server is using over here. And you'll notice that the server is using .3 as its default gateway, and that is the IP address we're giving to this logical sub interface. So every time a frame, imagine a frame, and we'll look at one here in a second. Imagine a frame that's being sent from switch 1 up the trunk. Well, if it has a tag of 2 or 3, If it has a tag of 2, this logical subinterface is going to be handed that packet and says, deal with it. If that frame has a logical tag of 3, it'll be handed to this logical subinterface for it to go ahead and deal with and process it. So let's walk through the configuration process here on R5. The first thing we're going to do is we are going to bring up FA00. And also, one other thing, let's go ahead and specify the MAC address, the hard-coded MAC address that comes by default. Let's go ahead and configure it to be all 5s, 0055 and all 5s the rest. That way when we see that MAC address, we'll know who it belongs to. Next, we're going to create the 2 logical subinterfaces. And we can name these subinterfaces anything we want, FA00.90 or FA00.2000. It doesn't matter. What really does matter is that the VLAN tag that we identify inside of that subinterface, that's what controls which frames are going to be processed by this logical interface. Think of a little guy sitting at the entrance of this interface handing all frames that are tagged with 2 to this subinterface and all frames that are tagged with VLAN 3 to this logical subinterface. So the config for the subinterface is really simple. Encapsulation .1q for VLAN 2 and an IP address. We're done. That's it. So there's not any commands that says trunking on the actual router. So on the switch we said trunk. On the router we simply created .1q subinterfaces and we're done. Now we're going to do the same thing for the FA00.3. We'll create the FA00.3 subinterface. We'll specify that this subinterface is handling any frames that come into the physical interface with a tag of 3 for VLAN 3, and we'll put an appropriate IP address on that subinterface. See, the whole goal here is to provide inter-VLAN routing. And this router on a stick, why is it called that? Because it's got the router with one physical interface. It looks like it's sitting there on a stick. We're going to do logical routing between the 2 subnets. So now that that's all in place, let's just do a couple show commands to verify. Let's do a show ARP to look at the ARP cache. And at the moment, R5 knows about its 2 logical interfaces, 2 and 3, and it sees it has the same MAC address for both. Now, how is that possible? You can't have duplicate MAC addresses. Well, the reality is we can't have duplicate MAC addresses in the same VLAN. But you see, this interface right here is a member of VLAN 2, and this interface here is a member of VLAN 3, and as a result, we can have the same exact MAC address, both borrowed from the parent, from the physical interface, because they're in different VLANs. Now, just for fun, let's go ahead and take this client on the far left over here, which is really just an iOS router pretending to be a PC at the moment. Let's do a show ARP. And in its ARP cache, it knows nothing except its own MAC address. And I also want to show you the server on the far right that we're going to ping here in just a moment. This is the server on the far right. We'll do a show ARP, and it has a MAC address. And I wanted to hard code these MAC addresses so that you could see this when we look at it with the protocol analyzer, that the MAC addresses for the router is going to be all 5s. For this PC on the left, it's going to be 1s and 0s. And on the server, which we're looking at here, is going to be 3s and 0s. So you can see it in the trace as it goes on. And just for grins, let's go over here on the left PC and let's do a ping of 30.0.0.10. And before I press enter, let's talk about the process of what very likely is going to happen behind the scenes. So now the fun part. This PC, when it does a ping to 30.0.0.10, what's the first thing that's going to happen? I mean, what does the PC think about? Does he think about, I think I'll buy a puppy? No, what they think about is this IP address, 30.0.0.10, which is the IP address of the server, is that local, meaning is it on my local network segment, or is it remote, meaning not on my local network segment? And the way the PC figures this out is simple. The PC looks at its own IP address, which is 10.0.0.10 with a 24-bit mask, and it believes that it's on the local 10.0.0 network. And if the destination IP address doesn't look like it's also on the 10.0.0 network, the PC thinks it's remote. Done deal. So what does it do after that? Well, the PC then is going to say, well, how do I forward this packet to my default gateway? We have a default gateway configured of 10.0.0.2. And the reality is the PC needs to know what the layer 2 address is of his default gateway, which is this logical sub interface in R5, and to get it, he's going to do an ARP request. That ARP request is fascinating. Check this out. The ARP request goes out from this PC into the switch. The source MAC address is the PC's MAC address. The destination address at layer 2 is a broadcast, because we're looking for an answer from the person who has that layer 3 address of 10.0.0.2 to determine what their MAC address is. So the broadcast goes into this switch port, which is assigned to VLAN 2, and the switch says, okay, new game, what do I do with this layer 2 broadcast? And the answer is, the switch is going to forward that to all other access ports who are also assigned to VLAN 2. So if I had 15 different VLANs configured on this switch, 15 different access ports and different VLANs, the broadcast on this local switch would only be forwarded to other access ports in VLAN 2. Any ports that were assigned to VLAN 17 or 18 or 19 or whatever would not receive those frames. And that's how the layer 2 switch is controlling the traffic and controlling the broadcast domain. It makes sure that VLAN traffic only goes to other ports in that same VLAN. Okay, so other ports that would also receive this broadcast are the trunks. So the switch is going to take that broadcast that it received here, it's going to tag it saying, hey, this VLAN, this broadcast came from VLAN 2, and forward it to switch 1. Switch 1, what does he do with it? Well, he gets that broadcast and says, I need to take this broadcast. The .1Q tag said it was for VLAN 2. I need to send this to all other access ports who are assigned to VLAN 2 and any other trunk ports that I may have active. So he's going to forward that layer 2 broadcast tagged with VLAN 2 out these trunk ports here. He's also going to send it up to R5. And that's almost where the magic happens. Check this out. R5 receives a VLAN tag traffic, an 802.1q tag on this broadcast, which was sourced by this device, and it hits FA00. And FA00 has a classifier. What's a classifier? Well, a classifier is just simply a sorter. Let's say you have a pile of $1 bills and $5 bills and $100 bills, and you want to sort them. Well, sorting them, somebody says, okay, I'm going to put all the ones in one stack, all the fives in another stack, and all the hundreds in another stack. You're simply sorting. Well, we have a sorter that's logically built into this FA00 interface. The sorter says this: if I see a .1Q tag come in that's for VLAN 2, I'm going to put it in this pile, and it logically hands it to this function on the router. If I see a tag that comes in for VLAN 3, I'm going to hand it to this logical subinterface. If I see a tag for VLAN 17 and I don't have any interfaces configured for VLAN 17, I'm simply going to ignore the packet and not do anything with it, because it's really not my business what's behind that VLAN 17 tag. I don't have any logical subinterfaces to handle it. And that's it. So when this ARP request comes in, the ARP request is logically sent because it has a .1Q tag of VLAN 2 on it. It's sent to FA00.2, who looks at it and says, oh my goodness, this is an ARP request. And it's looking for my IP address. As a result, we are going to source a packet, rather source an ARP response from this logical interface. It's going to have our source MAC address, and it's going to be sent back to the unicast MAC address of the PC who started it. So ARP requests are broadcasts, and the replies, because in the request it has the source MAC address of who wants it, the replies are unicast. So the reply would be sourced from FA00.2. It would be sent as a unicast down this trunk. It would be tagged with the .1Q tag of VLAN 2, because that's where it came from, that's who it's for. This switch would receive it, and this switch would then forward it based on its MAC address table, its forwarding table for VLAN 2. It would forward it down these trunk leaks, because that's where the source MAC address lives from the switch's perspective. This MAC address of this PC lives off these trunk ports. Switch 2 receives it, has a .1Q tag on it when it comes in, takes off that tag and says, okay, I need to forward this to the correct port, which is 1/2, and only if port 1/2 is a member of VLAN 2. Because if there was a MAC address that was assigned to some other, or a port that assigned some other VLAN, and that MAC address was there, the switch is still enforcing the boundaries, the layer 2 boundaries of only forwarding layer 2 frames inside of the appropriate VLAN. It's not going to forward it outside of the VLAN that current frame belongs in. So the response is going to come from the router through the trunk, through this trunk to this switch, and then finally be sent back to this PC. Woohoo! That's one ARP request. So once that ARP happens, we are then going to forward a packet to the router that's sourced from 10.0.0.10 destined to 30.0.0.10. Now when the router gets it, check this out. The router gets it, he says, wow, I know how to get to 30.0.0.10. I'm directly connected. It doesn't need a routing protocol or anything. It's directly connected to both of these networks, but R5 doesn't know what the layer 2 address is of this PC, of this server. So R5 itself would do an ARP request, sourcing it from its VLAN 3 subinterface and sending it out as a broadcast. This server would respond, and then at that moment, this PC would know the MAC address of R5, and then R5 would also, from the second ARP, would know the MAC address of the server. Now, once all that's happened, then the actual packet can be forwarded, and the packet can be forwarded across from the PC to the router down to the default, or down to this server on VLAN 3, the 30.0.0.10. We also should lose a couple of pings due to the ARP resolutions. So we're very likely to lose one ping here as ARP happens here, and lose one ping here as ARP happens here as well. So out of 5, we'd very likely lose 2 packets due to 2 separate ARP requests that are happening at the same time. Okay, that was a mouthful. So just for fun, let's capture this as we go forward. And I'm going to capture all the traffic on this trunk link right here. So right after we do the ping, we can bring up a protocol analyzer and take a look blow by blow, play by play at exactly the packets and frames that are going back and forth. So all we have to do here is press enter. And it would be really boring if it didn't work at all. So, okay, well, good. There's our 2 missed pings because we had 2 ARP requests, one here and one there. And now that ARP has totally been resolved, we could probably ping again and have 100% all the way. And if we wanted to verify the trace, we do a trace route from our IP address, which is 10.0.0.10, all the way out to 30.0.0.10. And it would show us that the first hop is 10.0.0.2, which is our local interface of our default gateway, and the final destination. So we have basically one router and then the final destination of 30.0.0.10. Let's take a look at that protocol analyzer and go through step by step what just occurred. There is a lot of activity on this little network with a bunch of spanning tree and keep lives and a lot of other protocols that are in use, but let's zero in on the focus point for this discussion, and that is the conversation of the ping between this PC and this server. Our first interesting packet, or frame I should say, is an ARP request. And this ARP request is when the PC said, I'm looking for the MAC address. Let's take a look at the details here. I'm looking for the MAC address of 10.0.0.2. So it doesn't know what that MAC address is. It's looking for it. Now that frame got sent into switch 2, who identified it as belonging to VLAN 2 because of the access port it came in on. He forwards it down the trunk, tagged with VLAN 2. Switch 1 forwards it up the trunk, tagged at VLAN 2. And that's what we're seeing right here. So in the Ethernet header, layer 2, it says the next protocol to hand this up to isn't IP. That would be 800. It's 802.1q, which is protocol 8100. So it hands it up to the next level, if you will, in this protocol stack. And the 802.1q header, the most important aspect is right here saying it belongs to VLAN 2. And as a result, this logical subinterface, which is paying attention to VLAN 2, is going to process that ARP frame coming in. So here's the ARP request. And you know what the most polite thing to do? If there's an ARP request and somebody's looking for your MAC address, the appropriate response would be to reply. And that's this next frame right here. This is the ARP reply. Look at the source MAC address. The source MAC address is 555555, which we hard-coded on R5, and the destination is unicast because we knew from the ARP request who the requester was, so the reply is a unicast. We also know that we're sending it from VLAN 2 or .1q 802.1q VLAN 2 managed interface, and so we're going to tag it as we send it down to the switch that this belongs in VLAN 2, and that part is right here. So as the response comes down, even though it's unicast, it's assigned to VLAN 2. So switch 1 already knows where this MAC address lives. It lives off this trunk, and VLAN 2 is allowed, so it forwards it this way. Switch 2 knows where this MAC address lives because it learned it on FA1/2. Now, switch 2, just to be aware, switch 2 is not just going to blindly forward this frame out this port. The reality is, because it came in with a .1q tag that says this belongs to VLAN 2, it's only going to forward it out this port to this client if it knows that that's where that MAC address lives, and that port it's about to forward out on is also assigned to VLAN 2, because the switch is the one responsible for maintaining and controlling the layer 2 VLAN boundaries. If that MAC address, this guy right here, lived off of another port that had been assigned to VLAN 17, for example, the switch would not forward it out that port because the VLAN and the MAC address both didn't match up. So in this case, we're not doing any trickery or anything else. The switch forwards the response out this interface, and now this device knows what the MAC address is of its default gateway. And the MAC address is 55, 55, 55, 55. So that's the initial ARP request that goes on. So let's scroll down a little bit further. Here we have some spanning tree that's going on. And let's take a look at the next echo request right here, or the next. So here's our ping packet that's coming in. Source from 10.00.10, the PC destined for 30.00.10. Now, when this router got that, it said, oh, you know what? I don't know what the layer 2 address is of this server right here. So the router made its own ARP request, which is what we're looking at right here. And this is where we also, by the way, lost that second ping, was as R5 was trying to resolve the layer 2 address of the destination on that same local subnet. So here we have, again, the Ethernet frame that says the source is 5555, the MAC address on the FA00.3 subinterface. It's actually the same on both. And the destination is a broadcast. We are handing, this is a 802.1q tagged frame, hence the Ethernet header specifies what the next layer is, and it's pointing to 802.1q. In the 802.1q header, it says this belongs for VLAN 3, because the router said, oh, I know how to reach the 30.00 network. The device I'm trying to reach is on that network. That's why it sourced it from this logical interface. And it's a request. And it simply says, I'm looking for whoever has the IP address of 30.00.10. I need your MAC address. So that broadcast goes to switch 1. Switch 1 forwards that to switch 2 and switch 3, because switch 1 doesn't know where it needs to go. It just forwards it on all trunks that are allowing VLAN 3. And switch 3, because it does have ports in VLAN 3, is going to forward it out this port. The server hears it, and as a result, the server is going to respond back. So this is the server responding back, saying my MAC address is 30.30.30.30. And as it gets sent back into the switch port, switch 3 forwards across the trunk tagged as VLAN 3. Switch 1 forwards it back up this trunk port, because that's where it knows the MAC address of 55.55.55 lives. It also tags it as belonging to VLAN 3, and router 5 receives it, identifies, oh, this is a VLAN 3 tagged frame. It's going to be logically processed by FA00.3. At that point, R5 now knows the MAC address of the PC, and it puts that into its ARP cache. And then the next Icmp packet that it gets to route to that device is going to be successful. So we lost one ping here on the ARP on this side, one ping here on the ARP on this side, and then once the ARP cache was built, all the other traffic went forward. So if we scroll down a little bit, we should see a bunch of Icmp echo requests and replies. So let's take a look at this. This is fun. So let's take a look at this request. This request is sourced from 10.00.10 to 30.00.10. And how come we're seeing it twice? Look at that. Why are we seeing twice before we see any response? And the reality is the ping request goes from the PC up to the router, and then that same request is being forwarded from the router to the server. So take a look at the Vlan tags. On the initial one, we have a VLAN tag of 2 as it went from the PC up to the router. And then from the router to the server, it came down on VLAN 3. So it went whoot, whoot. And so we have 2 requests. Really, it's just 1 request caught on the wire twice as the packet went up to the router on this one physical cable and then back down from the router out to the server. And then we're going to have 2 replies. So we have a reply from the server that comes in on VLAN 3, and then from R5 to the PC, it goes out from the router on VLAN 2. And that repeats approximately 3 more times, and then we have a boatload more of spanning tree and everything else. So that's a tutorial on not only how to configure a router on a stick, which by the way is super easy. You configure this guy right here as a trunk port, and you configure logical sub interfaces for the VLANs you want to support, and you are done. One other aspect is you want to make sure that these VLANs, VLAN 2 and VLAN 3, are existing, meaning they exist on these switches, because if a switch receives a frame for VLAN 17 and the switch doesn't have any knowledge of any VLAN 17 whatsoever, it drops the frame and will no longer forward it. And that is a big problem that sometimes comes up when you're using transparent mode for VTP. So if you're using VTP and every switch knows about every possible VLAN, you'll never have that come up. But if you have an issue where they won't forward, it's very likely some intermediate switch may not have that VLAN in existence, and that would stop the traffic. I appreciate you watching. I've had a lot of fun. Our next video, by the way, is I'm going to show you how to take this router and completely remove it. And we'll do inter-VLAN routing on switched virtual interfaces, which are integrated into the physical switches. I'll see you in the next one.